All right, so thank you very much for that introduction, John, and thanks to Bio-Rad for inviting me. And it's early, so we'll try to make it through. So as John mentioned, my topic is evaluating the impact of an out-of-control event, especially in the context of changing quality specifications. So what is an out-of-control event? An out-of-control event is when the lab receives a QC failure to indicate an out-of-control condition, which is a problem with the measuring system that could be leading to erroneous reports making it into the patient medical record. So these are my disclosures, and John mentioned some of them. I do have leadership positions in the CLSI, and I will be mentioning some CLSI documents. So these are the learning objectives for the presentation. We're going to identify the steps to recover from an out-of-control event, discuss how to evaluate the impact of an out-of-control event on patient results, and we're going to use the concept of allowable total error to discuss this. And then we're going to outline approaches for preventative action if we happen to find that our lab's QC program is insufficient to identify an out-of-control condition, or if the quality specifications have changed, for example, in response to the new CLIA PT acceptability criteria. So the primary reference we'll use for the presentation is CLSI C24, Statistical Quality Control for Quantitative Measurement Procedures. So this document has a number of recommendations for designing an effective QC strategy, for selecting appropriate QC materials and QC frequency for your laboratory, for establishing QC target means and target standard deviations, for troubleshooting QC failures, and also how to recover from an out-of-control event. So this slide shows the normal process we perform in the laboratory. So the blue bars represent patient sample results. And then, so we're measuring patient sample results, and then with some frequency we measure QC materials, so that's the black bar. If the QC material is within our acceptability criteria, then we are assured that the measuring system is performing as expected. However, if we receive a QC result that does not meet our acceptability criteria, then that could indicate that the measuring system is not performing as expected, or we have an out-of-control condition. So the document, C24 document, goes through a systematic step-by-step process on how to recover from this type of out-of-control event. And it's broken down into two phases. And so here I've shown phase one. The first step is to actually detect the analytical measurement system error via a QC alert. And this requires that the lab establish a QC program that is sensitive enough to detect when an out-of-control condition is present. The second step is to immediately stop reporting patient results into the medical record, because of course we don't want to issue erroneous results that the physicians may be acting on. The third step is to investigate to determine the root cause of the problem. The root cause is the fundamental defect in the measurement system that is contributing to potentially erroneous results. We need to know the root cause in order to implement the appropriate corrective action to correct the problem, which is the last step of phase one. So here's an example from our lab. This is step one, detecting the analytical measurement system error via a QC alert. So here you see lipase results. These are Levy-Jennings charts for level 1 and level 2 lipase QC. And so you can see that historically the assay was in control, meeting our acceptability criteria. And then the lab received a 2.5S failure, where 2 QC results exceeded 2.5 SDIs from the mean. So the lab receives the alert. So this is just an example of our QC program in action. The C24 document recommends that we set our target means and standard deviations with sufficient amounts of data. We need at least 10 days worth of QC data for a new lot to set the target mean. And the document recommends that we need several months worth of data to set the target SD. And this is because in that target SD, we want to incorporate as many sources of normal variation in the assay when it's performing as expected. So things like multiple calibration cycles, multiple maintenance cycles, multiple reagent wedges, for example. Of course, when you launch an assay, you're not going to have several months worth of data to set the SD. So you can set a preliminary standard deviation target and then revisit it after a couple of months that that assay is in production and refine the SD if needed. The document also recommends that QC multi-rules should be established to identify out-of-control conditions quickly. So our lab uses the 1.3S rule, the 2.5 within control rule, the 2.5S across control rule, an 1.5S rule. This is when 8 values exceed 1.5 standard deviations from the mean in a single control material. That will fire an alert, and it indicates development of a slow trend. And then also the range 4S rule, which is when the range between 2 consecutive QC points in a single control exceed 4 standard deviations from each other. That rule detects imprecision. So numerous publications have performed these kind of power analysis as seen in this slide that really show that the use of QC multi-rules really establish the best combination for detecting an out-of-control condition while minimizing the false alert rate. So the false alert rate is when the tech receives a QC failure, but there is no out-of-control condition present. And we want to minimize the false alert rate because we don't want tech spending precious labor resources chasing down problems that actually aren't real. Okay, so we've detected the analytical measurement system error by ensuring our QC program is sufficient to issue a QC alert when we have an out-of-control condition. We then want to immediately stop reporting patient results by turning off auto verification in our LIS system if that's what we're using. If not, we can use a manual process. The next step is to investigate to determine the root cause of the problem. And I've listed the most common problems that we experience in my laboratory. So one very common problem is a problem with the QC material itself. So the vial has been taken in and out of the refrigerator too many times, it's been left on the bench too long, and it's degraded. Another common problem is a problem with the reagents. So we have a reagent wedge on board the instrument, and it has degraded even though it's still within its onboard stability claim. And so this happens with particular lots of reagent. This happens with, for whatever reason, one single wedge of reagent. This can happen with a particular shipment of reagents. So we have to look out for that. There could be a problem with the calibration, so maybe the lamp energy has declined some on our spectrophotometry instrument, and the instrument needs to be recalibrated, or the assay needs to be recalibrated. We could have an instrument problem, so common problems include etching in the sample probe or need to realign the sample probe, leaks in the pumping system or tubing, clogs in the waistline. We've had mixers break. There could be, the root cause of the problem could be due to inadequate maintenance, so we're not performing maintenance frequently or aggressively enough, or of course, improper procedures. So I think one thing that we found is really helpful for our technologists is to develop a systematic approach for root cause investigation, because techs, especially if they're new, can be overwhelmed. There's so many causes of QC failure, and we really wanted to develop a tool for them that they can start, they know where to start, they know the next step to perform for their investigation. Of course, this type of systematic approach will be unique to each measuring system, each laboratory, and maybe even each assay. So the first thing we have them do is repeat the QC. Now, this is not a repeat of the same vial of QC on the instrument. That is a useless task and not going to provide any information. We ask them to walk into the refrigerator, get a new vial of QC, place that on the instrument, test. If that passes, if the QC value is close to the target mean, then we can be relatively assured that the problem is just with the QC material itself and there is no measurement system problem. If the value is far from the target mean or fails, then we know that a problem with the measurement system itself is likely. So the next most common thing for our lab is that the reagent wedge on board the system has degraded. So we ask the techs to next replace the reagent wedge. If that causes a pass QC, great. If not, go ahead and recalibrate, because that's the next most common problem. Prepare a fresh calibrator, recalibrate. If QC passes, great. If not, go through a step-by-step troubleshooting process that we designed for each measurement system. If the tech cannot accomplish troubleshooting and fix the problem, then we call technical service. So that kind of step-by-step process is really helpful, especially for new people. Some additional tools for investigation of root cause include looking at the QC multi-rules, so which rule failed, does that give us any insight? Look at our Levy-Jennings chart, is this a shift or a drift, which would point us toward a road of further investigation. What about routine lab records? We have calibration records, reagent lot change records, maintenance logs. Maybe we put on a new reagent lot and suddenly we have a QC problem. Other lab records, like our 6-month linearity checks and our among instrument comparisons. So if we have a QC failure on one instrument and see, oh, the 2 other instruments, their QC is about to fail, we probably have a problem common to all those instruments, like the reagents. Another really useful tool is the peer group QC programs. So of course, Bio-Rad has one. This one happens to be Sysmex. And this is where the lab will submit its QC data in real time. And you get a real-time comparison to your peer group on your particular reagent lot. So this can be very useful for troubleshooting. So once we've identified the root cause, we now want to implement corrective action to correct the problem. So here I've shown that. For this lipase problem, we have put on a new reagent wedge. And when we put on a new reagent wedge for this assay, the manufacturer recommends recalibration, so that's what we did. And you can see that QC came back into the acceptable range. So most of the time, we would say, great, we fixed the problem. We can recommence patient testing, which is true. But this is not the end of the recovery process. We still have the entirety of phase 2 to work through. This is where we need to evaluate the impact on previously reported patient results. So remember that we were reporting patient results. We had a QC failure. That means sometime before that QC failure, there was an out-of-control condition. Our measurement system had an error. So we could have reported already erroneous results into the record, and physicians could have acted on that. So once we evaluate the impact, if it's clinically significant, we need to take steps to mitigate patient harm, which involves contacting providers and issuing corrective reports, and then ultimately implement preventative action to prevent the problem from occurring in the first place. So here's our little graph of our QC results. So here we have a QC result failure, and the root cause was found to be a problem with the measurement system. Therefore, patient results before the time point of the QC failure could have been erroneous, and we need to go back and repeat those patient results from the time of the QC failure to the time of the last acceptable QC. This could be 3,000 results, depending on your lab's volume. So you may want to go back and repeat in subsections of time to find out where did the error occur, and then repeat all the patient samples after that. So how do we evaluate the impact on previously reported patient results? Because we don't want to issue corrected reports if we don't have to. Maybe the error is small, not clinically significant, and issuing many, many corrected reports is very disruptive to our environment, also a waste of tech resources. So we developed this little tool. It's basically just an Excel spreadsheet. And here, in the first column, the techs can put in their original result, and then they can enter the repeat result. The tool calculates the difference between the repeat and the original result and compares it against an allowable error. So for lipase here, I've set the allowable error to 10%. So if the difference exceeds 10%, then there's a little script that says, instructs the tech, yes, please issue a corrected report. If the error does not exceed the allowable error, the script says, no, do not issue a corrected report. So this can be used in the middle of the night. They don't have to call anybody, and it allows expedited review and automated decision-making for when a corrected report is needed. But the whole key to this, we'll take some questions at the end. Yes, and I will show you, I will show you the calculations used. Yes. Okay, so what is allowable total error? So it's an analytical quality goal that sets a limit for the combined effects of all sources of error, including analytical imprecision and bias, that are tolerable in a single measurement. And there are a number of CLSI guidelines that describe this concept. So there's the CLSI C24 document, the CLSI EP21 document, which is on total analytical error, but it does discuss allowable total error, and it's currently under revision. as well as a new document, CLSI EP46, which is under development. And that document is actually going to be dedicated to discussion of allowable total error. So how do we use allowable error limits? So we use them to establish quality specifications for numerous lab activities. They're super useful tools. So you can use allowable error to establish acceptability criteria for method validation, for designing your statistical QC program, which Dr. Nichols will talk about, for evaluation of the impact of an out-of-control condition like we've shown here, and also to determine acceptability criteria for proficiency testing, which is what CLIA has done. They have actually used allowable total error goals to set their new criteria for proficiency testing in combination with some data from state-of-the-art testing. So the European Federation of Clinical Chemistry and Lab Medicine in 2014 had a conference in Milan where they discussed how to establish allowable total error goals. And so allowable total error goals based on clinical outcomes is the preferred approach. So your error goal or error limit should not exceed the change of analyte concentration in disease or a change of analyte concentration required for therapy. And in fact, it should only represent a portion of that change. So you can get that data from professional practice guidelines and clinical trials data. You can also establish the allowable total error on biological variation data. So biological variation is the variation of an analyte when a patient's health status is stable. So that's the natural variation of an analyte, and it's different for different analytes. You can find this information in databases like the EFLM database and the Westgard database, and I will show you an example of this, because this is actually what CLIA used to establish the new PT acceptability criteria. You can also use state-of-the-art assay performance. This data can be obtained from the manufacturer's package insert, the scientific literature, and the lab zone validation data. And so please look forward to the EP46 document coming out. It's going to discuss each of these approaches thoroughly. Here's just an example. So this is the EFLM biological variation database. So I've given you the the website link at the top. And what this database does is you can enter your analyte of choice. So here I've entered lipase, and the website returns biological variation studies that you can see under the reference section. And the ELFM has actually performed a meta-analysis of those studies and provides the within individual biological variation. This is the average variation of lipase within an individual. And also the between individual biological variation, which is the average variation of lipase between individuals whose health status is stable. So we can use this to calculate the allowable total error limits. So here, this database is nice because it has a little button at the top, analytical performance specifications. You can click that button and get the allowable error limits. It's using this equation shown. So you can see that the intra-individual variation and the combined intra and between individual variation estimates are there. And there's a few factors, 0.5 and 0.25 between those estimates. And that tells you the specification level that you want your allowable error to represent. So the website gives specifications of minimum, desirable, and optimal. And those factors in front of the intra-individual CV and between individual CV combined with intra-individual CV represent which specification you want. So here I've chosen desirable, and that is 50% of the intra-individual biological variation and 25% of the combined estimate. So your total allowable error cannot exceed those percentages. So if you want to move to the minimum specification, those factors get higher. If you want to move to the optimal specification, those factors get lower. So that's how that's calculated. So here we see for desirable, total error goal is 12.9%, and optimal is 6.4%. So I considered how lipase is used in my laboratory, the clinical utility, and decided to choose the midpoint, which is 10%. So that's how I figured out what to put in this tool to tell techs whether or not to issue corrected reports. Now, if I wanted to switch to the optimal of 6.4%. So here my quality specification or allowable error limit has changed. That will impact the number of corrected reports they need to issue for the same amount of difference when we repeat the QC after we've corrected the problem. So changing the allowable error limits changes the impact on the activity that you're applying it to. So as John stated, these are some examples of the Nuclea allowable error aligned acceptability criteria. So they use this allowable error concept, incorporating biological variation and some data on state-of-the-art assay performance to come up with these goals. So the process for evaluating impact on patient care after PT failure is the same as you would do for evaluating impact on an out-of-control condition. You follow the same exact process. So the last step of the process for recovery from an out-of-control condition or PT failure is to implement preventative action. So frequently, part of the preventative action is to redesign your QC program to identify the out-of-control condition more quickly, or if you're not getting the appropriate alerts, to get the QC alert when you have an out-of-control condition. So to redesign the QC program, you can increase frequency of QC analysis. You can change the QC target mean or target standard deviations. You can add additional levels of QC materials. All of these will help improve the sensitivity of your QC program. And you can also use the allowable total error goals to establish your lab's QC approach. And Dr. Nichols is going to talk about the sigma metrics in context of allowable total error and how you can use this to adjust your QC rules. So in conclusion, we've discussed the steps to recover from an out-of-control event. This is a systematic process. Phase 1, detect the error, immediately stop patient testing, investigate and identify the root cause of the problem, implement corrective action. That's not the end of the process. You then move to phase 2, where you're evaluating the impact of the problem on patient results using allowable total error, mitigate patient harm by calling providers and issuing corrective reports, and finally, implementing preventative action to prevent the problem from reoccurring. So allowable total error is a very useful tool. It can be used to evaluate impact on patient results after an out-of-control event, or to make improvements to your QC program to detect error conditions more quickly and also respond to changing quality specifications. For example, if you find your lab is failing PT based on the new CLIA specifications. Okay, so that's the end of my presentation.